Okay, so here we are in CoCalc looking at the induction handout. So it should be in your handouts folder under induction. And we're talking about the natural numbers and about induction in Lean. So first I want to talk about how the natural numbers is defined in Lean. So I've put this in this namespace so that Lean doesn't complain that I'm defining it again, because this is how it is defined in the library. So the natural numbers is the type, or so in this course, of course, we're conflating types and sets. It's the type or the set that has these two special features. So first of all, it has this element 0 that we know of as the first element of the natural numbers. And it has this function that goes from the natural numbers to the natural numbers called successor. And here it's abbreviated suc. And as you remember from the lecture outside of Lean, we talked about how sometimes in mathematics, the natural numbers are defined to be the set that has these two special features and nothing else going on. And sometimes the natural numbers are defined in a different way, but proven to have these two features. But as you can see here, the natural numbers is defined to have these two features. Okay, so just a note that we can write the natural numbers as just nat, or Blackboard bold N, which we can write as just backslash capital N. I think there are even more shortcuts for that. So we can write these for the natural numbers and they mean the same thing. They're interchangeable. Okay, so here we're opening the part of the library that has facts and features about the natural numbers that we can use. And now we're going to talk about how to define functions recursively. All right, so we want to define this function that I'm calling count by threes recursively. So it takes in a natural number and it spits out a natural number. And I want the value at 0 to be 0, at 1 to be 3, at 2 to be 6, at 3 to be 9. So I want to basically count through by threes like you did when you were 5 or something. 0, 3, 6, 9, 12, etc. So of course, this is the function that just multiplies each natural number by 3, but I want to give a simple example of how to define a function by induction. Okay, so we have to do it just as we would on a piece of paper. We say where the function sends our first natural number 0, and then what it does to each successor. Okay, we use a syntax with these bars, and we say here that at 0, count by threes at 0 is equal to 0, and count by threes at the successor of n is equal to count by threes at n plus 3. Okay, and so note that here we don't write count by threes of 0. It's kind of implicit, the count by threes part. So we're saying at 0, send 0 to 0, send the successor of n to the value at n plus 3. Okay, so this is a function, of course. We just defined a function. But I want to point out that it's also a mini program, or just a very basic program that takes in an input from the user, a natural number, and returns another natural number, which is what we've just defined. So we can see in Lean that it can evaluate, it can run this program, and we can run this program on the input 5 and ask what comes out, and it's 50. We can also see it over here. And we can also run this program on the input 100, and we see the expected value of 300. So we can see, for you programmers in the class, we can see a little bit of how to write programs in Lean. And I just want to point out that Lean is a fully functional, fully fledged programming language where you can write any program that you want to. And here we're just seeing the tip of the iceberg of what's possible in that vein. Okay, so moving on back to functions and induction. The first thing I want to point out before we move on is just that this phrase successor of n suc n and n plus 1, they mean the same thing. They're interchangeable in Lean, so you can write whichever one you want to in the exercises. Okay, so now let's talk about how to prove things by induction in Lean. So let's suppose we have a predicate P on the natural numbers. So remember that in Lean, to declare a predicate on something, we define it as a function from that thing to the type of proposition. So here we're declaring a variable p that stands for a predicate on the natural numbers. Okay, so say we want to prove that p of n is true for all n. We want to use induction, which is maybe what you would expect to do in a case like that. So let's say here we have it written out. We want to prove that p of n is true given some arbitrary natural number n. Then we can do induction. We can call induction in the following way. So we can type this command, nat.rec underscore on. That's just a command that's telling the computer, okay, we're going to use induction. And the next thing we have to write is a variable. So we're writing the variable n to tell the computer that we want to do induction on this guy n. Okay, so it's just like the written proofs that we saw in those lectures. The first sentence I think I had for every written proof was something like, we proceed by induction on n. So this part here is like the phrase, we proceed by induction. And this phrase here is on n. Well, I guess there's an on here anyway, but we have on n. So we're doing induction on n. And here's also a hint that recursion and induction are versions of, or can be seen to be two sides of the same beast, I guess. Here it's not called induction, it's actually, I think this stands for recursion. So we're doing recursion or induction on n. And we have to supply, of course, two proofs. One here, that p of 0 holds. And here we have to supply a proof that for all n, if p of n holds, then p of n plus 1 holds. So it's exactly the same as we're used to. And we can check the exact form of what the computer is expecting, of course, by writing an underscore. So here we see that we need to give it a proof of p of 0. And here we see that we need to give it a proof that for all n and n, if p of n is true, then p of the successor of n is true. Okay, so I have some assertions that these things are true. So suppose we have, maybe from a lemma or from some other reason, we have a witness, BC, so BC stands for base case here, a witness that p of 0 is true. Then we can just tell the computer here that p of 0 is true. And say we have a witness here, this stands for inductive step, that for all n, if p of n is true, then p of n plus 1 is true, then we can just put it here, and the computer will accept this as a proof of p of n for all n. Okay, so now let's look at an example. And so this example, like a lot of induction problems, involves some calculation, which is a bit, I don't want to say tricky, maybe tedious, more tedious in Lean than normally. And so I won't require you to do this in this problem set, but I do want to talk a little bit about it because you might choose to do something like this for an extra credit problem. So we're going to be talking about a particular, what's called a tactic. And these tactics are explained in depth in section 9.4 and chapter 18 of the Logic and Proof textbook. So I'm not gonna really explain this in depth, but go there. It has a very good explanation. Okay, so here I have a lemma that I'm going to need for my proof that's coming up. So I'm just calling it my lemma. It takes in two natural numbers and a hypothesis that count by threes of n is equal to 3 times m, so it's divisible by 3. And from this, we're going to prove that count by threes of successor of n is equal to 3 times n plus 1. So it seems very reasonable. And we can prove this using the following tactic. So a tactic is a way, like a little kind of module, I guess you might say, in Lean that makes it easier to do proofs of a particular style. So we're not doing the proof in the most straightforward way that Lean expects, so we're using like a little functionality of Lean that lets us do the proof in a slightly different way that makes it a little bit easier for us. But it can sometimes be a bit harder because you have to remember exactly how these individual tactics work. Okay, so this one's called calc, and it lets us write a calculation very similarly to how we would on a piece of paper. So we want to show that count by threes of successor of n is ultimately equal to 3 times m plus 1. And so we do this in the following way using this tactic. So we first say that count by threes of successor of n is equal to count by threes of n plus 3. And that's just the definition here of count by threes. You can see count by threes of successor of n is equal to count by threes of n plus 3. So here we put the justification like we normally do on a piece of paper, though here we have to really put a justification for everything. And the justification for this fact, like most facts that are really obvious, is just REFL, just reflexivity. Okay, then on the next line we put dot, dot, dot. And note that these dots, I made this mistake once, these dots do not have spaces between them. If you put spaces between these dots, it won't work. Okay, so on the next line, we say that this expression, count by threes of n plus 3, is equal to 3 times m plus 3. And this is using our hypothesis H. So H lets us replace this first guy by 3 times m. And so I'm saying that I'm doing this by rewriting H. Okay, so I'm not going to explain exactly what rewriting is doing. If you want to know more about that, read section 9.4. Okay, now I want to think about this expression, and in particular 3, as being 3 times 1. So I'm going to tell the computer, okay, let's write it as 3 times m plus 3 times 1. And again, that's by reflexivity because it's so obvious. And then we're going to say, okay, to the computer, factor this guy, factor out the 3 so that we get 3 times m plus 1. And here we're rewriting by this fact left distributivity, which comes from the library and is telling us basically that we can distribute 3 through this sum of m plus 1. Okay, so this is how we can produce a calculation in Lean. And I just want to point out something, which is that there are some steps here which you would not normally write on a piece of paper. So Lean requires more information, as I'm sure you're used to by now, than a human would. So we usually write in Lean things more explicitly than we would on a piece of paper when we're just writing for a human being. So for example, I think that most people would skip this step on a piece of paper, but Lean Lean requires that you write this step. So I just want to point that out sometimes. If things aren't working, it's just because you need to write something that you think is obvious for Lean to accept what's going on. Okay, so now let's work on this proof. So the statement says that for an arbitrary natural number n, basically that count by threes of n is divisible by 3. So to be more precise, we want to say that there exists a natural number m such that count by threes of n equals 3 times m. Okay, so we want to do this by induction, of course. That's what the whole lecture is about. So we're going to use this command. We have to in order to do induction. And we need to give the computer the variable that we're doing induction on. So that's n. And we have to give the computer these two proofs. One that our statement is true at 0, and one that if it's true at n, then it's true at n plus 1. Okay, so let's work on the first one first. So here we need to prove, we can of course ask the computer what to prove. We want to prove that there exists an m and n such that count by threes of 0 is equal to 3 times m. So what you should do first here, I think, is to think about, of course, you're going to want to use exist introduction. So you're going to have to come up with an m and then come up with a proof of the equality. So what should the m be? Of course, it should be 0 because count by threes of 0 is 0. So it should equal 3 times 0. So I think we should prove this by writing a have statement. So let's say that we have a fact that count by threes of 0 equals 3 times 0. And we need a justification like this. And because these both just compute to 0, we can use reflexivity. That'll be a proof. Okay, so now here we're seeing an error but I'm pretty sure that this proof is correct. So just to check that I haven't made any mistakes, we should write sorry. And then we can see, in fact, we haven't made any mistakes. It was just the fact that we hadn't yet finished a proof. That's why the computer was complaining. So always write sorry if you're getting errors to make sure that you haven't yet made the error, that it's just because you haven't finished the proof yet. Okay, so now we have to produce this exist statement. So we have this statement here that is almost our exist statement, but just with the 0 here instead of the m. So we have to use exist elimination to turn our statement S into this exist statement. So we're going to show that there exists an m in n such that count by 3's of 0 equals 3 times m from, now we want to use exist intro, and the m here should be 0, right? That's what we just proved. So it should be 0, and then we have to give it the reason why this equation holds when we plug in 0, and that's of course s. All right, so now that part of the proof is done, and we have to do this next part of the proof. So if you forget exactly the form of what's supposed to go here, you should always write an underscore, and we see that it's a for all statement. So as usual with for all statements, there's just one thing that we're allowed to do, which is to, or one thing that we should usually do, which is to write assume. So let's assume that we've got an n and n, and let's check what's going on. So we see what we hopefully expect, which is the same thing, but without the for all there. So this is an implication. We see that this guy is implying this guy. So we have to assume that this guy is true. So let's assume, let me put this parenthesis down. So let's assume that we have an m in n such that count by 3's of n equals 3 times m. Okay, now again, we can put an underscore, and it's telling us what we expect. But I want to pause for a second and just say, just point out what's going on, which is that we have our natural number n, we have our hypothesis that the statement holds at n, and now we're trying to show that the statement holds at the successor of n, or n plus 1. Okay, so that's hopefully exactly what you would expect. That's exactly how induction works. Okay, so we have an exist statement. We want to prove an exist statement. I think in a case like this, what we should always do is use exist elimination so that we can get a hold of this m and a hold of this hypothesis and use that to do something. So let's do exists elimination on our exist statement, h1, and now here's a perfect opportunity to use the $sign so that we don't have to deal with too many parentheses. And now, if you forget exactly what to do now, you can write an underscore, and we see, first of all, it's a for all statement. So we want to assume, let's use the variable a, just like the computer. And let's check again what's happening. We see that this is an implication statement. It's this guy implies this guy. So we can assume the first guy. So let's assume h2 that count by 3's of n equals 3 times a. And now again, let's check. Okay, so now we see that we have the same goal as before. We need to prove this exist statement. And now we have 2 extra hypotheses, which is good. More hypotheses is always good. All right, so to prove this exist statement, we of course would expect to use exist.intro. And so we need to come up with the appropriate m that makes this true. So this is exactly where my lemma comes in. My lemma says that count by 3's of successor of n is equal to 3 times m plus 1. Okay, so if count by 3's of n is equal to 3 times m, so here it should actually be a that we're talking about. So if count by 3's of n is equal to 3 times a, then count by 3's of n plus 1 is equal to 3 times a plus 1. So let's record that fact. Say count by 3's of n plus 1 is equal to 3 times A plus 1, and this is exactly the lemma. So we want to plug in N and M, and let's see, H2. Made a mistake here, which is that this should not be M, but should be A. Good. Okay, so let's see what's left. So what's left is the same as before, but now we have this extra hypothesis. And now we just want to turn this A plus 1. We want to use introduction on this A plus 1 to say that there exists an M such that this holds where M is in place of A plus 1. So now we can show our statement. So we want to show that there exists an M and N such that count by threes of N plus 1 equals 3 times M from exist intro, and now we want to plug in A plus 1 for M, and we have to give the computer also the reason why this is true if we plug in A plus 1, and that's S. All right, and now we see that the proof is correct because we don't have any errors, so we know that we're done. All right, so that's it for the lecture. Now I just want to talk about the exercises that I've assigned. So I just want to point out first that this file and the homework file are exactly the same. Just put them together. Maybe that's a bit easier. So there are 3 exercises. The first one's a bit different than what I've assigned before. Here I want you to actually define your own function called triangle. And just to note that here I have some axioms about triangle, but the computer complains because it doesn't know what triangle is. So once you've defined that function here, you will see these errors disappear. Okay, for the second one, I want you to prove this statement. So replace this sorry with a proof. And you can use these 2 axioms, which are basically giving the calculations to you, so you don't have to calculate anything yourself. And here, for this problem, number 3, I've defined another function. And I again want you to produce a proof by induction. And I've given you these axioms to avoid any calculation. All right, so that's it for today. If you have any questions about this material, please put it in the discussion section, in the discussion entitled, I think, Lean Induction Discussion.